13 is a lucky number. Let's start. Hello, everyone. It is my great pleasure today to welcome Professor Ornella Mattei. So Ornella is, renowned for her work on space-time metamaterials. And most specifically, she introduced, together with Graham Mitton, some theory of field pattern metamaterials. And Ornella, the field is yours.
Thank you very much, Sebastian. First of all, I would like to thank Bogdan, Sebastian, and Muammer for the invitation. The title of this talk seems a little bit mysterious, but all I'm going to do is to talk about time modulation in materials. Specifically, in this talk, I'm going to focus on a very specific type of time modulation that is a sharp time modulation. So what I mean is if you take, for instance, a one-dimensional element, in this time diagram, you have a space-time diagram. So the horizontal axis is space, the vertical axis is time. So at time t equals 0, you start with a material that has properties alpha 1, beta 1. And then you do something from the outside. You change the external applied field so that your material will turn from material 1 to material 2 with properties alpha 2 and beta 2. So in this talk, I'm not going to focus on any specific type of wave phenomena, anything that can be described by a second order differential equation, linear, as the one that you see here, where clearly alpha and beta will be functions of time. So can we make in real life a time interface? Well, that depends on the type of wave phenomena you work with. For instance, the very first experiment where they were able to observe a time interface was in the context of water waves. What I'm going to show is a video taken by the YouTube channel of Emmanuel Ford. So what you see here is a tub of water from the top. And what they do is to drop an object. In this case, is the model of the Eiffel Tower. And what happens is that will create a water wave. And then they create this time interface by effectively changing the gravity by accelerating the tap upwards. And then it will create a time interface in the wave that is going from the source toward the edges of the tub will split into two. One that will refocus towards the center where the source is, and the other one that will keep it traveling in the same direction. So let me show you the video. So this is the mission when the Eiffel Tower is dropped into the tub. Then you see here when they change the effective gravity. And indeed, you see the creation of two waves, one that goes in the same direction and one that goes back, and that refocus at the source. So this was the first experiment in the context of water waves, but you can realize some sharp time interfaces also for other wave phenomena. For instance, if you look at the case of elastic waves, this is an illustration of an experiment that was performed by an Italian group at the Polytechnic of Milano in collaboration with Massimo Ruzzene at the University of Colorado in Boulder. So here you see a beam with piezoelectric patches. And the way they modulate the properties of the beam is by changing instantaneously the current in these patches. Way more complicated is the realization of a time interface for electromagnetic waves due to the nature of these waves. I think the only experiment up to now where they were able to observe a time interface at the for microwaves was done in the group of Andrea Alu a couple of months ago. This is an illustration of the experiment where you have a transmission line with these switches that are placed with a spacing that is way smaller than the wavelength of the wave. So in this experiment, what they see again is that if you have a forward wave here depicted in blue, then this will at each time interface will split into two waves, a forward wave that will keep going in the same direction, and a backward wave that will keep traveling in the opposite direction. So if we go back to the space-time diagram that I showed at the very beginning, and then you see that if you have an incoming wave that hits a time interface, this will split into a reflected wave and a transmitted wave. And we are able to determine the intensity of these two waves by using some continuity conditions at the interface. Specifically, what is conserved here is the continuity of the wave as well as the momentum. And so you can find the UR and the UT. And you see here that they depend on the gammas that are the wave impedances. And specifically, you see that if the two wave impedances are equal to each other, then there is no reflected wave. Very similar to what happens in the case of a space interface. So let's actually compare the two cases, what happens at the space interface and what happens at the time interface. So if you just compare the two equations, you see that they are basically equal to each other if you replace the space variable with time and the coefficient alpha with the coefficient beta. So if for the space interface, we have the continuity of the amplitude of the wave as well as the flux, then when you apply these transformation, x in t and alpha in beta, you do end up with the continuity of the amplitude and the momentum. So we have the reflection and transmission coefficients for both cases. But here, what is the main difference between these two is that given that for a time interface, you don't have conservation of flux, you don't end up with conservation of energy. So in general, when you have a time interface and a pulse that propagates through it, you see that energy is going to increase in time due to the fact that you have to pump energy into the system in order for the material to change properties from alpha 1 beta 1 to alpha 2 beta 2. So that's the difference number one. You do have that the energy associated with the wave will increase in time as you keep modulating the material properties in this way by changing instantaneously the properties through an instantaneous change of the applied field. But that's not it. There is another difference that I'm going to show by looking at a time laminate. So by time laminate, I mean a material where, for instance, at time t equals 0, you have properties alpha 1, beta 1. And then instantaneously at time t equals t naught, you change those properties into alpha 2, beta 2. And then again, after another period of time t naught, you go back to alpha 1 and beta 1. Actually, you don't need to do this periodically, but okay, so let's see what happens to a pulse that propagates through these time laminate. So we start at time t equals 0, say with a pulse moving to the right with intensity ui. And then we apply our time interface we will see a split in the pulse into two. And if we only look at the intensity of the of the pulse that keeps going in the same direction, so the wavefront, basically, you see that the intensity is completely determined by the wave impedances of the two materials, gamma 1 and gamma 2. Then we apply another time interface, so we have another switch, so we'll have a further splitting of the wave, and we can write down the intensity of the wavefront in this scenario. Now, if we keep doing this, we'll see that the intensity of the wavefront will have this expression where n is the number of switches from material 1 to material 2, and m is the number of switches from material 2 to material 1. So this is it has an exponential behavior. So as time goes by, you see that the intensity of the wave will also increase exponentially together with the wave. So what I'm interested in is the following question: how to avoid the exponential blow up of the overall amplitude of the wave, so that, for instance, you can think of using these materials as materials where you can, as devices where you can store energy. So you cannot do anything in the linear regime to keep the energy finite. If you look at the propagation of pulses of these type, so energy will keep increasing, but that could be a good thing if you think about storing that energy and then harvesting later on. But if the propagation of the pulse is unstable because of the amplitude of the pulse will increase, the overall amplitude of all the scattered waves as well as the wavefront will increase in time, then you cannot do much with it. So that's why we want to keep the amplitude of the pulse and the scattered waves finite. Well, one easy answer to this question is, well, if you look at the case where the two wave impedances are equal to each other, then you're going to have a no reflected wave, both at the time interface and at the space interface. So in that case, you have that if you go back to the case of the time laminate, the pulse will propagate without changing its amplitude in time. It will just change shape. That's it, as it goes through one interface, time interface to the next. So what if the two wave impedances of the two materials are not equal to each other? Well, in that case, what we propose is to introduce a spatial microstructure that is designed in such a way that you will not have the exponential blow up of the amplitude of the wave. So this is the question that I tried to answer with my collaborator Vincenzo Gulizzi from the University of Palermo. But actually, the starting point to answer this question goes back to my work with Graham Milton. Because back then, even though we were trying to solve a different problem, we did find some very special microstructures for which the wave propagates without increasing in amplitude. So let me show you some examples. So the first example that we found is called a space-time checkerboard, and it's made in this way. So in you start at time t equals 0 with a one-dimensional element that is made of alternating segments of material 1, material 2, material 1, and material 2. Then at time t equals t naught, you are going to instantaneously change material 1 into material 2 and material 2 into material 1, and so on. So if you plot this in a space-time diagram, you do end up with a space-time checkerboard. And if you don't choose the material properties in any special way, then this is what happens when you send in a pulse and it splits at every time and space interface. You end up with a cascade of disturbances that is kind of difficult to keep track of. And here, the intensity of the wave will not be overall finite, but it will increase exponentially in time. So what we understood was that you need to find a geometry so that the scattered waves will interfere in a positive way so that they will kind of like cancel each other, and the overall amplitude of the wave will be constant. We achieve that by introducing this type of geometry. So it's still a space-time checkerboard, but here we use this very restrictive assumption that is that the two wave speeds are equal to each other. So C1 equals C2. But that's not enough. You also need to create the geometry in such a way that is commensurate to the wave speed. So you see here that if the time modulation occurs every unit in abstract units, then the width of each rectangle has to be equal to C. And you see that here you do end up with a periodic pattern of characteristic lines, and we call these a field pattern. So now let's make sure that actually the wave propagates at constant amplitude when we send it through a material of this type. So to do that, given that this pattern of characteristic lines is periodic, what we can do is to compute the solution only at certain moments of time and certain points. We don't need to compute the solution everywhere in the domain. So what we did was to compute the transfer matrix associated with a unit cell of this domain. Here you see that the solution at the point K in the unit cell M at the moment of time n+1 is related to the solution at point K prime in the unit cell M prime at time n, so at the previous time step, through this transfer matrix, where the entries of the transfer matrix are found by computing some Green's functions. So clearly, given that for this problem, the two wave impedances are equal to each other, you'll have that t depends only on the wave speeds. So t will depend only on the wave impedances. Given that the periodic pattern of characteristic lines is PT-symmetric, you have that the matrix is a PT-symmetric. And here you'll see that the type of PT-symmetry you have is always unbroken. What I mean by it is that regardless of the wave impedance, the wave will always propagate without increasing its amplitude in time. This is what I mean by unbroken PT-symmetry. Indeed, if we send in a pulse in this structure, this is what we get. So here we have a left-going pulse. This axis is time, this axis is space. And what I'm doing is to plot the solution at every time period at those points that I chose. So this is not the solution for any x and any t. It's just a discrete solution. But you see that the pulse propagates with constant amplitude at the edge of the field pattern, whereas in the middle, you have these oscillations that will keep occurring with the same amplitude. All right, then we started playing around with these geometries. And the first thing that we did was to say, okay, what if I don't have two materials, but I have three materials? So here what I did was to change the material in this square that before was a light gray into a dark gray. So this is material 3, so it has a different wave impedance, but still it has the same wave speed. So here I'm again in the case where the 3 component materials have the same wave speed, but have a different wave impedances. Well, actually nothing changes compared to the previous case. You end up still with unbroken PT symmetry that does not depend on the wave impedance ratio. So if I plotted the solution for this case, you would see exactly the same solution that I showed a second ago, this one here, same thing. All right, so let's make things a little bit more complicated and consider a 4-component space-time checkerboard. Here again, I am looking at the case where the wave speeds are still equal to each other. That's why you see that the slopes of the characteristic lines do not change when I go from one square to the next. Well, here things get interesting because you see that for some combinations of the 4 wave impedances, you have unbroken PT symmetry. So the wave will propagate with a constant overall amplitude. But for other combinations, you will end up with broken PT symmetry. That means that the wave will have amplitude that will exponentially blow up. So let me show you this. So this is the case where I choose the gammas so that the condition of PT symmetry is unbroken. In this panel here, you see the eigenvalues of the transfer matrix, and indeed, they are all on the unit circle. On the right here, you see the propagation of a pulse, and you see that it propagates without increasing its amplitude in time. And at the bottom, you see 2 eigenmodes, one that is periodic and the other one that is not. So let's see what happens when the condition of PT symmetry is broken. Well, in this case, what happens is that on top of the eigenvalues of the transfer matrix that lie on the unit circle, I also have some eigenvalues that do not. So these correspond to a couple modes, one that is increasing in time and the other one that will decrease in time. And if I send in a pulse into the material, when I choose a combination of the wave impedances for which I have broken PT-symmetry, I see that the amplitude of the wave will exponentially increase in time. This graph is in a logarithmic scale, and that's why you see a linear increase in time. As I said, we played around. So at this point, you can say, okay, very nice, but the wave speeds of the materials are supposed to be equal to each other. So what if we remove that assumption? Can we come up with another field pattern for which I end up with something similar? The answer is yes. This is an example of another space-time checkerboard where I have 3 materials. So the light gray, the white one, and the dark gray one. And the wave speeds of these 3 materials has to be very special in the sense that the ratio between the each pair of wave speeds has to be equal to an integer. Here I choose a 3, but it could be 2, 4, whatever. Here we find that for some combinations of the wave impedances, the condition of PT-symmetry is unbroken. So you have a propagation of the wave with constant amplitude, but for others, you do not. So if I plotted the graphs for these case, you would see exactly what I showed for the previous case. So I'm gonna skip that, and I'm gonna show you another space-time geometry that is not a space-time checkerboard. So here you have a matrix of material 1 with inclusions of material 2. Here, you find that the condition of unbroken PT-symmetry is achieved only when the 2 wave impedances are equal to each other. That is basically when you have a no reflected wave. Otherwise, for any other combination, you do have a broken PT-symmetry. So here, pulse will propagate by increasing its amplitude in time. All right, so if we look at all these geometries, the question then is, what is so special about the ones for which we have always unbroken PT-symmetry? What do they have that the other space-time geometries do not have? Well, what they have is the following. So the wavefront and any scattered wave will always have to encounter a space interface followed by a time interface between the same materials. And this has to occur in a field pattern material because otherwise you don't have that nice interference between the scatter waves. But let's see, for instance, an example. Let's only focus on the wavefront and suppose that we have initially an intensity and amplitude of UI. So if the wavefront crosses a space interface from material 1 to material 2, then by using the transmission conditions at the space interface, we can find the amplitude of the wave after the crossing. And that's going to depend on the difference of the wave impedances. Now, if the wave that now is in material 2 crosses a time interface between material 2 and material 1, and I compute the amplitude after this crossing by applying the transmission condition at the time interface, I'll see that what I get back is exactly the amplitude of the initial pulse. So let's check whether this design principle applies to the microstructure that I showed to you earlier. So this was the very last example that I showed where we did not have unbroken PT-symmetry. And so in this case, unless the wave impedances are equal to each other, we do have that the wave increases its amplitude in time. But the reason is that if you look at where the arrows are, we have some characteristic lines. In this case, I'm just looking at the wavefront that goes from a from a space interface to another space interface. So they violate this design principle for which a wave exiting a space interface should enter a time interface in order to maintain the amplitude finite. So that's why this design does not work for our purpose. So let's go back and check the other designs. So in this example here, we found that for some values of the wave impedances, we had the broken PT-symmetry, for others unbroken. Well, the reason for that is that if you look at the wavefront, so if I only look at the edge of the field pattern, the wavefront will go from a space interface to a time interface, and then back to a space interface, and then time interface. So the wavefront satisfies the design principle, but the scatter waves do not. So if you look at the characteristic lines in the dark gray region, you see that those connect space interface to space interface. So that means is that in special situations where the gammas are chosen properly, these will not cause any problem and you will still have a constant amplitude, but in other cases that will fail. So the two examples, the only two examples that in the work with Graham Milton, we found to be so special to always have unbroken PT-symmetry for any wave impedance were these two. The space-time checkerboard with 2 phases and the space-time checkerboard with 3 phases, where in both scenarios, the wave speeds of the two materials have to be equal to each other. Here, if you check whether our design principle works or not, you see indeed that every single characteristic line goes from a space interface to a time interface, and it does so by always going from material 1 to material 2, and then from material 2 to material 1. All right, so now the question is, can we generalize the type of microstructures that we have? So first of all, you don't need to have a space-time checkerboard. You can generalize this structure in this way, where delta is a design parameter that you can choose as you like, and it takes values from 0 to infinity. So if we look at what happens here, let's now perform a full-scale analysis so that we can actually check how the amplitude of the wave changes at any x at any t. So if we do that, this is what happens when we send in a Gaussian. I'm just looking at Gaussian pulses here. I'm not looking at the plane wave solution. So here we start at time t equals 0 with a pulse, and here you see actually 3 graphs. In red, you have the propagation of this pulse in a space-time checkerboard of the type that I showed here, okay, where you choose a delta parameter as you like. The result is not going to change. Then in blue, you see the result of the propagation of the same pulse in a time laminate that have exactly the same properties as the space-time checkerboard. And then in orange, you see the result in a homogeneous material, where the properties of that material are chosen to be the same as the material properties of the material where you center the Gaussian at time t equals 0. So what you see is that as time goes by, as expected, the amplitude, the overall amplitude in the time laminate will increase exponentially in time, whereas the solution in the space-time checkerboard is a constant. So we have that the wavefront will always have the same amplitude, and the oscillations in the wake of the wave will always have the same amplitude. Here you don't see very well the homogeneous solution because it's basically 0 up to the wavefront, and then the solution of the space-time checkerboard is right on it, so that's why you don't see it. But basically, what's happening here is that the wavefront is propagating as if it was in a homogeneous material. I have to be, I'm kind of cheating here in the sense that I am plotting the solution at periods of time after I send in the pulse. So every time I plot the solution, I am in the same material. So here the wavefront is always in material 1. If I had to plot the solution in between, so when the wavefront is in material 2, then you would see that the amplitude changes, but it changes in accordance with the transmission coefficient that you have at the space interface between material 1 and material 2. So what is happening is that the wavefront will change as it goes through the as it travels through these material, but always with an amplitude that is constant in each constituent material. And if you wonder what happens to the energy, this is the energy associated with the homogeneous case, constant. Then you have the space-time checkerboard in red and the time laminate in blue. It looks like the space-time checkerboard energy increases linearly, but actually that's an exponential function. It's just that the growth rate is way smaller compared to the time laminate, and that's why it looks like a linear function, but it's an exponential one. Okay, now that we understood what the design principle is, we can come up with all sorts of microgeometries that will satisfy that design principle. So here, if you want to play around with the unit cell of the space-time checkerboard where the two phases have the same speed, you can come up, for instance, with another microstructure of this type. However, the condition for which the two wave speeds are equal to each other is kind of restrictive. So let's try to see if we can come up with something better. If we can come up with a geometry where the wave speeds are not equal to each other. So the most general microstructure we could come up with, this is the work in collaboration with Vincenzo Gulizzi, is the following. C1 and C2 are the wave speeds in the light gray material and in the white material. But then you do need a third material, that is the one in dark gray here, that has a wave speed that must be related to C1 and C2. Specifically, the wave speed in the dark gray material has to be C1 squared over C2, which is still a restrictive assumption, but not as restrictive as saying that all the wave speeds have to be equal to each other. Here, you still have a lot of freedom in the choice of C1 and C2. So let's see what happens here. What happens if we send in a pulse? Well, the design is such that each characteristic line will always go from space interface to time interface. And then again, time interface, space interface. And that always occurs from material 1 to material 2, from material 2 to material 3, from material 3 to material 2, and so on. So if we plot the propagation of a pulse in this structure, you see here that as the time goes by, the wavefront will always have the same amplitude, as well as the oscillations in the wake of the wave. So we did achieve what we wanted. If we plot the energy here, it does increase as usual, but at a rate that is way smaller compared to the previous cases. All right, let me see how I'm doing with time. Okay, yes. So now, what about 2D wave propagation? Well, if we are looking at a pulse that is unidirectional, like this one, well, then it's very easy in the sense that all you have to do is to extend the design of the microstructures that we propose in the 1D case to the 2D case. So in the top left, you see the design where the wave speeds are equal to each other. In the bottom corner instead, you see the design where the two wave speeds are not equal to each other, and you need that third material, the dark gray one, that has a wave speed that is related to C1 and C2. And here, if you send in a pulse of this type, trivially, you end up with a conservation of the amplitude of the wave, of the overall amplitude of the wave. But what if we have a pulse that is symmetric in X and Y? It's spherical. Well, these two designs are not going to work very well. And I'm going to show you what happens if you send in this pulse in the geometry in the top corner. So this is what you see. So in these graphs, the top panel represents this space-time laminate, whereas the bottom one, the homogeneous case. And in the middle, you see the amplitude of the wave as it travels through this material. Again, I'm looking at Gaussian. And what you see is something similar to what happens when you look at time modulation only. That is, the amplitude of the wave will increase in the wake, in the scattered waves. And that's due to the fact that we're sending in a pulse that is symmetric in X and Y in a geometry that is not. So we need to change our design a little. And what we can do is to extend the 1D design to the 2D design by making it symmetric in the X and Y direction. So here you see a matrix of material 1 with inclusions of material 2. All these cubes have the same properties. They are just in different colors to highlight the depth, the three-dimensional depth here. You can choose the design parameter delta as you like. If, for instance, you choose delta to be equal to 0, then you do end up with a proper space-time checkerboard, both in space and in time. So let's see what happens to a Gaussian when it travels through a material of this type. This is what we have. So in the left, you see the intensity of the wave from the top. And on the right panel, you see the amplitude of the wave as it travels through the material. So you see that the wavefront is actually changing amplitude as it goes, but it always does that in a way that we can totally measure, as well as the wake of the wave. And you see that given that we're working with field pattern materials, you do end up with these beautiful patterns in the propagation of the wave. All right, let's now compare these results of the space-time checkerboard with what you would get in a two-dimensional time laminate versus then the case of a homogeneous material. So you see that indeed, when you introduce the space geometry in a suitable way, the intensity of the wave is overall constant in time, whereas the one corresponding to the case of a time laminate will exponentially blow up. Here, though, the intensity of the wave, the intensity of the wavefront will not be exactly the same as the case of the homogeneous material. It will be a little bit smaller. Okay, now last thing that I want to discuss is the effects of noise. Because up to now, if we go back and look at any of these geometries, I'm assuming that the time interface occurs at very specific moments. If that does not happen, actually, let me go back to a case where I have the, here. So you see that if for some reason this time interface is not exactly here, but it's a little bit before or a little bit after, this is going to mess up the whole pattern of characteristic lines, so that will not be periodic anymore. So what it means is that the scattered waves will not meet right at the point where they're supposed to meet in order to interfere in a constructive way to keep the amplitude of the wave overall constant. So let's see then what happens when we introduce noise. Here we go. So first of all, let's start by introducing noise in the time laminate. The way we do it is by saying that the time interface, instead of occurring at, say, every 1 unit, will occur at 1 plus an epsilon that is taken randomly in a certain interval that depend on the standard deviation sigma. We follow the work of Emmanuel Ford and his group for water waves. So what they found, and this is confirmed by our results as well, is that interestingly enough, when you have a time laminate and you introduce noise, noise is going to be positive in the sense that if you see here in yellow, you have the solution in a time laminate where the modulation occurs at every, say, unit, every every unit. And then the other three graphs represent increasing level of noise from 0.03 to 0.09 for the value of the standard deviation. And you see that the bigger the noise is, the smaller the overall amplitude of the wave is. So if we look at the very last snapshot, you have that the wavefront will not be affected by the noise, but the wake will. And you see that the bigger the noise, the smaller the amplitude of the oscillations in the wake of the wave is. What about energy? Well, when you introduce noise, actually energy will be smaller. So in yellow, you see the case of a time laminate without noise. And then the other three curves represent noise in with different level of noise. Okay, so what happens when we introduce noise in our space-time checkerboard? Oh, here, by the way, I didn't specify this, but I'm looking at the one-dimensional case for the effects of noise. So when we introduce noise, we can already expect that things are not going to go very well, because as I said earlier, the scattered waves will interact in a way that will not be the one that is prescribed by the geometry. So they will not meet exactly the points where we want them to meet, and therefore the overall amplitude of the wave will indeed increase in time. So here you see in yellow the case where I have no noise, and then we increase the level of noise, and you see that the amplitude of the oscillations in the wake of the wave does increase in time. What happens then to the energy? Well, in yellow, you have the energy when there is no noise, and then the other three graphs represent the case where you do introduce noise, and you see that the energy does increase in time. So noise is positive, has a positive effect in a time laminate, but it does not have a positive effect in the geometries that we're looking at, for which the time interface needs to occur at a very specific moments of time. So this is all I wanted to discuss today. I think I have enough time for questions, and I thank you all for your attention.
Thank you very much, Ornella, for this wonderful talk, and I welcome questions from people in the audience. Feel free to ask any kind of questions, you know.